Well, thank you very much. Thank you for having had the patience of following my 2 first classes. So this one is for you. This is a talk, a specialized talk. And I want to report on some progress on something that is very dear to me and in general to people in Geneva, which is to try to compute critical exponent and ideally even conformal invariance of 2D lattice models. And so you know very well that Stas Smirnov had this marvelous successes, Rick also, for dimers, for Ising model, for percolation on the triangular lattice, side percolation. But that in some sense, these are models that works definitely better than others. Like we have difficulties generalizing these proofs to a bigger class of models like that. So a few years back, we started with Johann Manolescu, but then we quickly joined forces with Karol Kozlowski. We started a program that was intended in trying to prove conformal invariance in a slightly different fashion compared to the existing proofs. The idea being that, and I think, Rick, you will agree with me, that one of the big difficulties for conformal invariance using discrete holomorphic functions is, first, you need to have discrete holomorphic function, but then the boundary conditions are really difficult if you go beyond dimers and Ising, for instance. Already for Ising, it was one level harder maybe than for dimers, at least on Papaleon domains. And when you get to more general, like FK percolation, which Q not equal to 2 or 0, then it gets really nightmarish, and we have basically zero clue how to do it. So that's really a big problem. There is a second big problem, which is that we don't have true pre-holomorphic functions. They are only half discrete holomorphic, but maybe that can actually, maybe that's not the biggest problem. The biggest problem is really, to my impression, is the fact that the boundary conditions are nightmarish. So what we thought is that we would try to find a way that goes around it. We didn't find it. Just don't think that I'm going to announce conformal invariance. But you are going to see what we did still led you somewhere, in some sense, maybe farther than what we expected. And that's what I want to report on. So let me start maybe by telling you about the players in the game. So the 2 players, or maybe I should say the 3 players. So I'm going to tell you about FK percolation and 6 vertex model. But there is going to be another model that I want immediately to introduce, and that is going to be an oriented loop model that many people in the room know, but not everybody. So oriented loop model. And the model is like that. So you imagine that you have this green lattice, and on it, you have loops that can only touch but not intersect. So they are kind of avoiding loops like that. So you have collection of loops. And these loops are oriented. Okay? They have an orientation. So this is on the yellow. Okay? So on the yellow lattice, you get oriented loops. So let me call omega with this sign for this oriented loop. And the probability of this oriented loop model, every configuration will have a weight which is proportional to e to the 2i pi mu, number of loops oriented like that, minus number of loops oriented like that. So it's not a probability measure. It's a complex valued measure. Maybe let me not use, well, okay, let me use P, but it's not a probability. Okay, and a priori, for now, I'm not fixing mu. Okay, so it's just the weight is proportional to e to the 2i pi mu times number of loops oriented in one way minus number of loops oriented in the other way. Okay, and so this is the oriented loop model, and the good thing about this oriented loop model is that there are 2 natural operations you may do on it. The first one is you may forget the orientation. Just keep the information on the loops. And then when you do that, what you realize that each loop was coming with an orientation. So one time it was contributing e to the 2i pi mu if the loop was actually oriented in one way, and e to the minus 2i pi mu if it was oriented in the other way. So if you forget about the orientation, you get here something, I'm going to do it like that, with a clause like that, just to refer to the fact that it's only the loops now. So a model of loops on the yellow thing, lattice. So it's still on this one. Actually, it will always be on this one. And the probability of this loop model without orientation then is proportional to a parameter to the number of loops now, and this parameter will be e to the i2 pi mu plus e to the minus i2 pi mu. So I'm going to call it square root q. So it's going to be square root q to the number of loops. And here square root q is just 2 cos 2 pi mu, right? Well, it's good because this loop model, it's appearing in a very natural context, which is that what I could do is on the white lattice, I could be looking at percolation. Okay, I could assume that they are like, oh, that's a terrible choice of color. That I have some edges that are blue. These are the edges in my percolation. Some edges that are white, those are those that are not in my percolation. And what I can do is that for those that are white, I can actually draw the dual edge associated to it. And then when I just draw the loops that bounce, that never cross any of the two configurations, primal or dual, I obtain a family of loops on the yellow lattice. Well, guess what? If you start with the standard Fortune-Castellan percolation at criticality on this white lattice, on Z2, the loop model you obtain is exactly this one. So this is just this loop model that I defined. It's just the interfaces, if you want, between primal and dual configuration of critical Fk. Okay? So I get Fk out of just forgetting the orientation here. But there is a second observation, a second thing I can do is that I can take these oriented loop things and I can forget about the loops. Just remember the orientation that it gives to each edge. Okay, so here it's forgetting orientation. Here it's forgetting the loop. And when I do that, I obtain family of, I obtain an omega arrow, which is going to be an orientation of the loops, and this orientation, an orientation of the edges, sorry. And this orientation of the edges, it satisfies something clear because the orientation came from loops. What I immediately get is that there are as many incoming as outgoing edges at every vertex. And this is a model that we know very well. It's called the 6-vertex model. You have 6 possible orientations. Configuration. And maybe let me just draw the incoming arrows. This is the first one. This is the second one. And then you have 2 things like that. So these are the only possible configuration you have. Here I only drew the incoming arrows. But now, when I look at that, so here for now it's the 6-vertex model, but I didn't tell you what are the weights. So let me get the weights for you. When I look at that, I also notice that this thing is e to the I pi over 2 mu times number of left turns minus number of right turns. Simply because any loop is having, so if it's oriented clockwise, it's having 4 turns on the left more than turns on the right. And if it's oriented the other way, it's going to be 4 minus term, minus 4 turns. Okay, but if you look at it like that, and you look here, what were the possible loop orientation that are coinciding with these things, with this configuration? Here, there is only one possible loop. The loops are determined by the orientation. You know that it's going to do like that. There is no choice. And it's going to be one left, one right term. So the weight associated to it is going to be 1. Same thing here. You have only one possible term. Here, 1, 1. These are all fixed, so you get always weight 1. And here, well, here you have actually two possibilities. Either you do like that or like that, and same thing here. And in this case, you get e to the I pi mu because there are two left terms. If you look at the orientation, it's going to be like that. This is the right, sorry. Two right terms. And here it's going to be two left terms. So the weight here is going to be 2 cos pi mu and not 2 pi mu. Okay? So 2 cos pi mu and 2 cos pi mu. So all of that to say, then Fk is directly related to 6-vertex model. Yes?
I'm not trying to understand the loop model. Is every edge covered by one directed edge?
Yes, yes.
If you have this Fk percolation, and suppose all the edges are blue, then there's no interface? Or?
No, there are interfaces because here, so I mean, that's a very good question. Here, this is a loop associated to it, right? So in your case, it will be only trivial loops of length 4. Yeah. So there is a link between Fk and 6-vertex model. This link actually is not due to me. It goes back to Baxter, Kellen, and Wu. And it's going to be something very important in what we are going to do. And it's also this direct link, in some sense, justifies why it's not surprising to find integrability on the Fk side, because you have it on the side of 6-vertex. I should say that here I was very, very not careful about the original graph on which I was working. If I work on the torus, for instance, then non-contractible loops are going to get a weight which is not square root q. Ignore this because really what I'm going to do, and this is something we know already for a long time, is I'm going to define everything. I mean, I'm not going to define, but in the paper, we define everything in full plane. So there is no problem anymore. And this was one of the goals, was to try to get rid of boundary conditions. So one big limitation of what we do is that we work in full plane. Okay? Very good. I mean, very good. I don't know. So that was to introduce the players. Now let me tell you, and maybe one proposition on this that I want you to remember, because as a probabilist, when I saw this first, I was a little bit freaked out because this is not a probability measure. So it's not a coupling between the two. It's just not a, I mean, it becomes a coupling when mu becomes purely imaginary, which would be what you would like to have when q is larger than 4. But when q is larger than 4, the phase transition is discontinuous, so it's not a place where you want to find conformal invariance, or you will be able to find conformal invariance or critical exponents. So in the regime of interest, which is q smaller or equal to 4, you get really a complex valued measure. But there is something which is pretty easy to see between these two things, is that, so the 6-vertex model, you can naturally associate to it a height function on the faces. The ice rule, the fact that you have 2 incoming arrows, 2 outgoing arrows, allows you to say, okay, I can define h plus 1 if, let's say, the orientation is that way, and h minus 1 if it's the other way. So in full plane, it only defines the thing up to constant, but if you integrate against functions, test functions that have 0 average, you will have no problem. Okay? So the 6-vertex model, you can see it as an oriented model or as a height function. Okay? Now, if you see it as a height function, there is a natural proposition that you can get, is that if you look at expectation of 6-vertex model of e to the I, and you integrate h against the test function f. Okay? Let's say it's piecewise constant on every face f. But you can also think of a smooth function and just approximate it by piecewise constant. So f has a 0 average. And in some sense, it's, ideally you want a smooth, compactly supported function, say. it's an easy exercise. I'm not going to prove it to you, but through this oriented loop model, going back to the FK model, you can actually rephrase this in the FK in a fairly elegant way. It's going to be product over every loop in your percolation loop model of cos 2 pi mu plus integral of f inside L divided by cos 2 pi mu. So what is it saying? It's saying that it's a product of weight on, I mean, it's like you twist the loop's weight with, I mean, in terms of how much of the integral of f it encompasses. Okay? This is really a fairly easy thing where you just go up. Here, a priori, you don't have any loop orientation, but I mean, the h can also be defined at this level, and then you just see that the orientation corresponds to going up or down, and you twist the thing, it works very easily. Why is this interesting? Because it tells you many things. It tells you in particular that if you understand the height function distribution here, you will get the scaling limit of these observables for the loop model. It's not all the observables you would like, probably, but it's already a bunch of observables. In particular, there is one observable that looks very good on this side, that imagine, so this is just a remark, imagine you can compute this, then what you could do is you can take h, which is basically putting a certain mass. So let me maybe simplify. So let me illustrate the power of this formula in a very simple context. So assume mu is 0. So mu equals 0 is q equals 4. Okay? So you look at Fortune-Castellan percolation with q equals 4. When mu equals 0, here you get product of cos integral of f, right? So in particular, if you take a small, I mean, two small balls of size epsilon at distance 1 of each other, say, or at distance epsilon n, sorry, at distance n of each other, okay? If you do that and you just take as a smooth function basically something that put mass pi over 2 here and minus pi over 2 here, okay? You spread the marmalade on your ball of size epsilon n. If you spread pi over 2 mass, then what you get from this formula here is that any loop that is surrounding this small ball, and only this small ball, will englobe a mass pi over 2, and the cos of pi over 2 will be 0. So what it tells you is that on this side, these loops, by the way, it's the same for minus pi over 2, they are forbidden. So by looking at the test function f, which is roughly pi over 2 delta of this ball minus pi over 2 delta of this ball, if you put this function here, you are basically going to get the probability that the two balls are connected in the original percolation that I wrote in blue. So, I mean, here I'm simplifying a little bit and I'm hiding a few things but what I want to illustrate is something that is going to be important to keep in mind for what is next, is that if you get here the convergence, and you will see that we will get the convergence to Gaussian free field, you are able to compute this thing. It's actually going to decay like epsilon to some power. And this power is nothing but the critical exponent of the two-point function for fk. And I did it for mu equals 0, q equals 4, but it works for every mu. So in particular, for instance, if one is able to get scaling limit of h then you get what we call a psi1 or alpha1. You get the one-arm exponent for FK percolation. For all FK percolation, not just Q equal 2 or Q equal 1. In particular, for Q equal 1, it would still be new because it's Bernoulli percolation on the square lattice. In fact, when you massage the thing a little bit more, you also get the two-arm exponent out of it, which is the probability of having a primal and a dual arm emanating from a point. And what we hope, I mean, we understand what is going on, we just don't manage to turn it into a proof, is that we hope to get the exponent alpha, which is the exponent for the free energy. I mean, it's a four-arm exponent for people who like Bernoulli percolation. And from those, you will get all the thermodynamical exponents, nu, beta, delta, etc., etc. So we have a hope, but this at this level is a hope. We have a hope that beyond these two, so let me maybe write it in another color, we would be able to get basically all the thermodynamical exponents. Okay, why did I say that? Because at this stage, in some sense, the story, so this looks like reasonable to get this exponent. What looks less reasonable, but would be absolutely fantastic, is can we actually get conformal invariance? So if I give you here the limit of h, can you recover full conformal invariance? That sounds more fishy. So I think for Q equal 4, it is not unreasonable. So for the special case here, in some sense, there is maybe a chance. For the other things, we fall back into problems that, for instance, Rick had with double dimer model, where it's you want to be able to have sufficiently many observables to determine the behavior of the loops. So we know that this is the case for double dimer if you take this extended class of observable that Dubeda introduced. But in general, you need to be careful to have sufficiently many observables. I cannot say for now whether these observables here, so you will get the full scaling limit of all these observables, whether this is sufficient. And I will definitely not bet my life on it on one side or the other one. I like this problem, but not at this level. Yeah. Okay. So that was the motivation thing. Now, what I would like to do in the second half of, is it a half? Actually, I don't know. It's 45 minutes or 1 hour? 50 minutes. Okay. So it's exactly half. That's. I'm going to try to tell you a little bit about the fact that we think we can get this convergence here, the convergence of H. Okay. Where do I stand here? I didn't organize my board well, sorry. So let's ignore this. So second part, scaling limits. Of H. Okay, so.
Can I have a question for
yes.
What you just said before? This function f you wrote, it has average 0.
Yes.
What kind of average is that? It's over space or over?
Space, over space. Yeah, it's integral over the whole of R2 is 0. And that's why I was careful to only explicit the Q equal 4 case. Because for mu not equal to 0, what you would like to put as a weight here, you have 2 pi mu plus. So you would like to put minus 2 pi mu here. Right? This is the thing that is going to guarantee that the loops get 0 weight. The problem is that 2 pi mu minus pi over 2 doesn't get, then the loops around it are not 0 weight. So you have to go around this difficulty, which I think is actually a fundamental one. I mean, there is a good reason why this is true, and I didn't want to go into details there. But yeah, you really need 0 average, and this is creating difficulties. Yeah. I mean, you have to pay a cost. I mean, we get around the problem of boundary conditions, but you there is a toll still to pay. Okay, scaling limit of h. So the story about this is a little bit strange because it started with a theorem. So I mean, we were not planning at all on going in that direction. What we wanted to do at the very beginning was to try to revisit the way physicists would prove conformal invariance, which would be to go prove scale invariance, prove rotation invariance. I mean, translation invariance is obvious. And then prove that once you have these two, you get conformal invariance. And we had some very cool argument that we never managed to fully write because we had a problem of critical exponent inequalities. I mean, we didn't know how to prove it. It's a true. We had a cool argument to go from scale, translation, and rotation invariance to conformal invariance. And we thought that even physically, this was an interesting argument because sometimes the justification, how you go from these three to the full conformal invariance, is a little bit fishy in physics. Okay, the fields are local, blah, blah. But so we liked this argument. And we thought, okay, since we are almost there with this argument, let's try to prove scale and rotation invariance, thinking that scale invariance will be the easy one and rotation invariance will be the difficult one because even physically, if you want to justify rotation invariance, you want already to say that, you know, in renormalization group, maybe there is a unique fixed point and therefore you... So why scale invariance for a physicist would be almost obvious, it's just, I mean, well, there is a limit, right? I mean, your thing, if you take the scaling limit, it should converge. Surprisingly, we actually got rotation invariance out of trying to get scale invariance. Sometimes you miss. We don't know how to get scale invariance. So the theorem that we got a few years ago, it's not published yet. I mean, it's on the archive for now 3 years. It's not submitted for the following reason, is that we are waiting to see exactly what we need for the GFF convergence. That's not that we are afraid of submitting it, just that we don't want to multiply the papers. So the theorem is, so Kozlowski, Manolescu, and there is two former PhD students on this paper. And the theorem is saying the following. It's saying if you look at FK percolation, so fix Q between 1 and 4. Normally, Q smaller or equal to 4 should be the right assumption, but we need the Fortune-Castle and the FKG inequality for our models. That's why we want to take Q larger than 4. And you look at the critical point. Then, actually, omega delta, I mean, the scaling limit of the model is invariant of the rotation. So let me write it like that. If I look at probability Fk, I don't know, let me simplify and say, for instance, I fix a certain number of points and I ask for a certain pattern, right? Like or maybe no, let me say I ask for a certain macroscopic event of the loop model. Since I worked with the loop model, let me stay with the loop model. Know something, I don't know, maybe there is a loop surrounding these 2 points, there is blah, blah. I mean, just a macroscopic event of this, and you look at the lattice with mesh size delta. So you look at the macroscopic event. What we prove is that this is equivalent in the limit delta tends to 0 to exactly the same event, but on a rotated version of the lattice delta. Okay, and this is rho theta of delta Z2. So you can rotate the lattice, you get the same limit. So we don't know that there is a limit, but we know that the things become equivalent. So any subsequential limit will be rotationally invariant. Okay?
So by this kind of event, you mean at some points, and then it's a certain...
Yeah, I mean, I don't know. It depends a little bit what what topology you like to put, but you could ask that the loops around like certain that you have macroscopic loops surrounding blah blah. You could ask that some quads are crossed by a portion of a loop. You can basically the full. I mean, anything you can think of macroscopically, basically you will get it. You could also look at the primal model and look at the probabilities that 2 points are connected or 2 endpoints are connected in certain, certain, you partition your set of points and you want that they are in the same clusters, for instance, or not in the same clusters. You can do whatever you want, basically. That's an equivalent, and this is delta tends to 0. Yeah. So this divided by this tends to 0 when delta tends to 0. 1. Whoa. You are listening. That's good. Or maybe let me write it in a more explicit way. You get something like that, in fact, with a certain exponent. I mean, of course, here, maybe if you take a very complex event, the big O has a constant in front, but yes. And actually, the proof of this, I mean, a posteriori, it's absolutely not surprising at all that we get rotation invariance and not scale invariance, because the proof of it relies on the star triangle transformation. And the star triangle transformation in these models is really a transformation that preserves the scale in some sense. And we don't have any, I mean, at least I don't know any. I mean, I'm also looking at the physicists in the room. I don't know any transformation that preserves integrability type transformation in this context that morally change the scale of your model. It's a very interesting thing to see whether there is one, but definitely the star triangle transformation, so the star triangle transformation in the case of FK percolation is basically saying, and there maybe I did organize a little bit better. The star triangle transformation is saying that if in my graph somewhere I have a triangle with certain parameter like probability for, so this is now really the original percolation on the white lattice, not the yellow one, okay? So let's say I have, Bernoulli percolation, and I have a triangle with three edge weight, P1, P2, P3. That's the probability that the things are open. In terms of connectivity in my graph, the model is completely equivalent to replacing this triangle by a star, just with different parameters. P prime 3, P prime 1, P prime 2. You have a condition on P1, P2, P3 in order for this to be true. But that's exactly what you would, that's exactly the critical parameters of your model. So if you are at criticality, you are allowed to change stars into triangle and vice versa. And so what you can do, and here it's really a very, 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 very high level proof of this, what you can do is you can try to look at your original percolation model and try to look at another model where, so above a certain layer, you look at something where the edge don't get weight P, C, but get a weight P of theta, theta being this angle, and P star of theta, depending on their orientation. And the thing is that basically the star triangle transformation allows you to transform this model into this model. What you would do is the following. You would here add an edge, very far right. You get a triangle. And then you transform this triangle into a star. I'm not going to do that. Let me try, but I'm pretty sure I'm going to fail. So if you do that, oh, wait. No, there is no way I'm going to. No, I'm not going to do it. So you transform it into a star. We all have our limitations. That's one of them for me. So transform it to a star. If you transform it into a star, here you will see a star appearing. Well, I can still do this part. Now you have a star here. You transform it into a triangle. And you keep going like that. And what it's going to do is that it's going to transform the first layer here. In some sense, this kind of squarish part is going to pass above this rectangular one. So it's going to transform slowly one thing into the other. So if you do that one layer, then you start below, you do it again, you are going to manage to make this rectangular part go deep into the square part. And you do it for every layer, so it's really a lot of star triangle transformations. But when you do it up to the end, you exchange the two configurations. And what you can do, and that's what we did, is that you can actually prove that this n cube, in fact, star triangle transformation don't change the geometry of the loops. You have to prove it. It's not easy, and it's not a priori obvious, but you can prove that it's the case. But that tells you something interesting, because you started from a model, you transform, you get to the other model, and you didn't transform the properties of the loops. But now this new model, notice that it has a symmetry, right? With respect to this angle, to this line. So that means that the original model had this symmetry. Because it's true for every theta, you get actually that it has all the symmetries by this line that are not at all aligned with the original thing, and it gives you rotation invariance. So that's basically the bottom line of this thing. And to me, this theorem would have no chance of existing if there was no link to 6 vertex. It's really integrability through the star triangle transformation, that, which is kind of a geometric rephrasement of Young-Baxter. So you really get this through this integrability deep inside. Yes?
So there are, of course, one critical models that also have a star triangle.
Yes.
Need an additional property for this to work, right?
Yes. So here, deep inside, there is going to be always the fact that you have qualitative properties like Rousseau-Seymour-Welch or things like that, that are going to actually tell you stay at criticality, and you use them. You use in particular the mixing property that these Rousseau-Seymour-Welch estimates give you, and which is kind of exactly would be failing if you look at off critical systems. Yeah, that's a very good question. I saw, yeah, okay, here. And then I'm coming. Yes.
You're critical. If you have some special points where the loop goes around the points, and
yes. Yeah, it's not, at least for me, it was not an easy result. Yeah. You have to handle all these things, indeed. So you have to handle the fact that the loops, if you look at the event that it surrounds certain points, for instance, or certain areas, it's typically not going to come very close to these areas. Then you will prove that it doesn't move much by the things, but then because it was not close to the points, for instance, it works. It's really, that's one of the difficulties. You point out one of the difficulties of this. Because, these loops do move. They just move subballistically. That's what you will get. So they don't move linearly. You could believe that if you have a loop like that, when you do this star triangle, it's kind of move with a certain speed, and it's going to be like pushed down by these successive things. You need to prove this is not the case. But indeed, you only prove that the speed of displacement is 0 in some sense. A little bit better than that. That's why we get the delta to the c. But then that creates exactly the difficulties you mentioned. Yes, you wanted to ask?
Yes. Do you know the value of this c, and does it depend on q?
The moral value of this c is that the speed of displacement should basically be, in fact, it should look like a Brownian motion. So it should fluctuate like delta to the 1/2, and then probably you can try to cook up what is the value of c. But it's there are like really many things that gets involved in the proof. So I never try to optimize it. So we have one c. It could be that it's because of the fact that you expect these Brownian fluctuations. It could be that you could guess the value of c depending on these fluctuations, so the 1/2. And definitely one parameter that will be important is the rate of mixing, which is related to the exponent alpha. So it's an exponent that we call iota in our scaling relation paper, which is a generalization of the 4-arm exponent for Bernoulli percolation that you can compute. So it could be that using iota and the prediction that this should fluctuate in a Brownian way, maybe you can get the thing. It's possible. That's I can actually think about it and tell you more about it. At least heuristically, I'm not sure. Other question at this stage? Yeah. Oh, okay.
Yeah. Okay. So is this Q between 1 and 4? Is 4 simpler than the other ones?
It breaks down exactly for the same reason, because then you become off-critical, and actually that's a good example. I mean, the star triangle transformation doesn't see that you are below 4 or above 4, and above 4 you will not expect rotation invariance. So that's typically one model for which it will be non-critical but still have this transformation. And of course, you cannot deduce rotation invariance there. So the Q equal 4 comes from the fact that we need to put in the system rotation invariance. Yeah. Q equal 1 is much less of a problem. I think actually that's a similar. So notice that this through, and then I didn't forget you, Alexei. This through the relation, the proposition that I didn't erase, but which is here, it also actually gives you rotation invariance of the height function for 6-vertex model. What I actually do believe is that you can do the whole proof on the 6-vertex side, and then Q equal 1 is not at all a barrier. It's something that you don't even see. I mean, C equal 1, which is much, much farther down the road, so C is 2 cos pi mu, should be the thing where our method would fail. So you should be able to get rotation invariance of 6-vertex model up to C equal 1. So A, B, C equal all to 1. So the square ice. Yes?
Could there be a version of this argument on the 6-vertex side?
Yeah, that's definitely what I believe. It's because now, and this was even less. Okay, I mean, we started to understand that at the time of this paper, but now we understand it much better. You need these qualitative arguments, this like good behavior of the level lines and things like that of your 6-vertex model. And now we have this Rousseau-Sem wedge on the 6-vertex side. We didn't have before. Actually, this one of the motivation was that for Fk, Q equal 1 is a barrier because you lose Fkg inequality, while on 6-vertex you lose it much later. So we wanted to have things on the 6-vertex side. So we have PhD students that work on this with Johan Manolescu. We have. So I hope that we will be able to report this because in particular, for what is going to be next, this will be the only barrier preventing you from going up to ABC equal 1 for the full scaling limit. Okay, it's very good there are questions. And it's very bad because I'm going to reach, yeah. So now, from that, a very surprising, so we didn't manage to do scale invariance, and the reason is that we don't have a transformation of this kind that changes the scale of the system. So we don't know how to compare the model on delta Z2 and the model on delta over 2Z2, for instance. We have no clue. But one thing that we noticed, which is very surprising, but I won't have time. Let me put. I won't have time to describe it now, so I'm just going to state the results.
Hugo.
Yes.
We have 10 minutes for questions, and we have taken like 5. So
well, but still I won't have time. But thank you for trying to send me. That's very nice of you. Yeah, so maybe I would give you a little bit of the heuristic. So the theorem, which I put with question marks, because again, we still have one lemma that is resisting. So, one lemma that is resisting may mean that it will never come up, but it's a lemma on the GFF. So normally, when you reach a lemma on the continuous GFF, you feel good. So the theorem would be the following. So it's that would be the players. So the lemma would say, take H delta, which is fix a 6-vertex with A equal B equal 1, and C belonging to something like, square root of 3 over 2, which I think probably is the thing that corresponds to Q equal 1, if I didn't mess up things. So the thing that corresponds to Q equal 1 here, and 2, which is the thing that corresponds to Q equal 4. And you look at it on delta Z2, okay? Let's look at H delta, which is the height function associated to it. And this converges in distribution to the GFF. I mean, to sigma squared that depends on C times GFF. Full plane quotient effect. Sorry? C equals 0 correspond to, no, I was saying Q equal 1. Oh, Q, sorry. What did I say, delta? So I meant Q. Yeah. So it basically for the 6 vertex associated to these models, you have GFF convergence. So here, what I mean by that is that if I test H delta against F, I get a random variable, and it converges in law to a Gaussian random variable with the right variance, which is going to be f of x, f of y, g of xy, dx, dy. And there is going to be a sigma squared. Don't ask me what's the value of sigma squared. I can find it back, but I always forget it. Okay? But it's explicit.
Can you comment it's kind of on the full plane, so without any boundary conditions at all?
Yes, it's full plane GFF and full plane 6 vertex model. So for Q between 1 and 4, or if you want for C between actually even 1 and 2, you can define the full plane 6 vertex model. It just converges. There is a unique infinite volume measure when it's flat, right? It's a flat 6 vertex. So this is the result. And yes?
The last author is this double M?
Yes, Piet Lammers. Yeah. Piet Lammers is Dutch as well. So this is the result. And let me just tell you in 5 minutes, because it's a very surprising story in some sense, how the things goes. Maybe I'm just going to move my hands, or maybe I'm going to write one formula and then move my hands. So how do we prove that? Here is this. Because in some sense, so rotation invariance is absolutely fundamental to prove this, but what seems very surprising to me is that it's sufficient. Because here, you get some scale invariance in some sense out of this. So why on earth rotation invariance on its own is able to do that? Well, one possible explanation is that what we did is wrong. So because of the question marks, that may be actually the... But definitely the lemma at the end for now doesn't, so it means that we will have made another mistake, which is also possible. But so basically, in order to do that, what you can try to do is you can try to look at H delta of U1 minus H delta of U2, H delta of U3 minus H delta of U4. Let's start with this first, right? You look at correlations between 4 points. I'm taking differences because I'm full plane, so I need 0 average. Only height up to additive constant is defined. And if you look at this, so you are still on your yellow lattice, right? What you can do, you are in full plane, or maybe you are on a very, another way of putting it is that you are in a huge torus. So you have transfer matrices. So you can write this in terms of transfer matrices, and in terms, in fact, of two things. So if you want to express, like if all the points were aligned in one row, you could use only the transfer matrix and get a formula out of the transfer matrix. If points start to be in arbitrary directions, then you need the transfer matrix plus a translation matrix that is going to be a matrix pushing you on the right by 1 step. But these two matrices, they are just the transfer matrices of two models. The one is our standard 6 vertex model, and the other one is a limit of the model which is with A and B not equal to 1, not equal together. So in some sense, what I want to say is that you have two matrices. Let's call them T and S, or T of pi over 2 and T of 0. Maybe that would be better. Two transfer matrices that commute, in fact. This is easy to see. So you can co-diagonalize them, and when you co-diagonalize them, you can express this thing. Basically, let me just write, because it's going to allow me to illustrate then later on what I want to do, but it's going to look like something like that. I'm going to tell you what this means, don't worry. Or maybe I worry, I don't know. So, what do I mean by that? X1, Y1,
I mean, y1, x2, these are just the increments between the coordinates of u1. So u2 minus u1 is just x1, y1, okay? Et cetera, et cetera. u3 minus u2 is blah, blah. And here, maybe I'm taking points in an order just to simplify for now. Now, what is this e to the minus a and e to the minus ib? Well, t of pi over 2 is symmetric, so all the eigenvalues are actually positive. And let me put them, I mean, are real, and let me put them between -1 and 1. So I write them as e to the minus a something. This is actually, they are all purely, I mean, they are on the circle, so e to the minus ib. And d mu ab is just a measure telling you, it's a product measure for the points, I mean, the eigenvalue points. Okay, because it's co-diagonalizable, you can put them on the same basis, and then you have, in some sense, for each element of your basis ei, you get e to the minus ai, and j, and e to the minus I bj, right? So then this is just sum of the Dirac on this point in the plane, okay? And, or maybe sum of the Dirac on this point. So now, in fact, this formula would be coherent with the GFF convergence if you had that, sorry? H is a height function. So now I'm just saying that it writes as, and here maybe there is a mu delta. So there is no edge anymore. Sorry? I mean, it's just this expression is equal to something that I can compute explicitly, just it's encoded indeed in this. Yes, so, yes, you are right. Thank you. Wow. I offer you coffee after. I'm impressed. So in fact, this is going to be coherent with, here you should get a difference of green function, right, to get the GFF thing. And this is exactly what you are going to get if you are able to say that d mu ab is first, so there should be, don't worry, I'm going to stop. If d mu is first, only putting weights on the diagonals, so I would like that B is equal to A d mu almost surely. In fact, then B would be plus or minus A. These are the two only options. And then the density is sigma squared dx over x, I think, if I remember, on the diagonal. And what is very strange is that here, maybe just to summarize, is that rotation invariance gives you a whole bunch of condition on that, because this is rotation invariant. So it gives you that this quantity, depending on the angles, is going to be constant. And from that, you can actually prove this inequality. So rotation invariance gives you that. And that, in particular, if you take, for instance, U1, I mean U2 tending to U1 and U4 tending to U3, it tells you that this is telling you that the thing is like, let's call it f of the distance. F of the distance is decreasing, okay, so let's say d times f of d is decreasing. That's what this thing will give you, in fact. And by going back a little bit to what Jan was saying, plugging into it, as just the fact that things are critical, you can prove that df of d doesn't tend to 0. So in some sense, this is going to tell you that df of d is asymptotically like constant over d. And that actually is sufficient. It's very surprising, but it's sufficient to tell you, okay, but then this is an equality here. And the sigma square here is actually the fact that f of d is going to look like sigma square over d. So you get the two other pieces of information from just this information that this thing doesn't go to 0. It's very surprising, but in some sense, rotation invariance seems to be giving you exactly what you need. So we never compute the eigenvalues, for instance. We don't know how to prove Young-Baxter, blah, blah, directly, I mean, to justify that this is okay, to actually even get the eigenvalue. We never do that, but we managed to look at this measure, this sum of Dirac, and prove that it converges to the right quantity. Once it converges, in some sense, one thing that you can see, if B is equal to A, absolute value of B equal to A, in fact, when you look at the Laplacian in one coordinate, you are going to see a B squared minus A squared. That is going to cancel, and it's going to tell you that everything is harmonic in each coordinate, and you can go to, prove GFF convergence. Okay, sorry, the end was way too fast. I just wanted to give you a glimpse at the thing, and maybe in 10 years you will see the paper. So thank you very much.